Hi everyone, Martin here. Welcome to the Inner Loop. This is the second part of the PicoDrone series. In this episode I'm going to talk about the oscillators. I want to talk a little bit about how I coded the oscillators, what my thinking was in terms of their mathematics, and then a little bit generally about how they work. So let's get started. Let's dig right into a little discussion about how the mathematics works. So before we start on the digital domain, I wanted to talk just a little bit about this analog circuit. It's a classic, an absolute classic, what's called astable oscillator. It consists of two transistors, and they're actually wired together in a symmetrical configuration. These transistors are both biased with a resistor so that they would both conduct. So this resistor here pulls the base up, and this would set this one conducting and this one conducting. However, let's pretend that one hasn't started conducting yet. Say this one. In which case this one is conducting, and this capacitor here, because it's conducting, this voltage here will be down here. It'll be very low. Because the capacitor is going to take a while to charge up, this point here will be very low, and this transistor will be basically clamped off and won't be able to conduct. Then what happens is this slowly charges up, and as the charge accumulates in the capacitor, the voltage here will rise. And as this voltage rises, this transistor will suddenly be able to start conducting. When that happens, this point here will go down to here, and it will switch this capacitor off. This transistor, it will switch this transistor off. Now, with this one switched off, this capacitor is going to start charging, and the whole process will go around again. And what this actually creates, because their transistors have a significant gain, is actually a square wave. I've actually built loads and loads of these over time, and here's a little example of one I built. It's got actually two of these astables and a mixer, and also a kind of like an envelope generator. So when it was actually working, it used to make little sort of beep sounds. The two variable resistors here are will actually vary what's called the RC, or resistor capacitor constant, and will change the frequency. By having two, you can also change the pulse width. So you can change the width of this pulse. You can make it sort of more like this. This kind of thing. And as a start to creating oscillation in the analog world, I think this is the first place that anybody would go to create a square wave, which can then be filtered. But this is completely not the way that it works in the digital world. So let's now have a look at the digital equivalent of this. How do I make an oscillation with a digital computer? Well, it's actually, for a square wave, very easy. All I need is a timer, or maybe two timers, and a digital output pin. My timer, this timer runs, says set the output low, and when time's up, set the output high. And then this timer runs, and then it says set the output low, high. So with some form of output stage or amplifier from my digital pin, I can create a square wave. What I'm going to need in my code is a sort of on-off. But a square wave isn't exactly what we need. The next thing we can look at is a saw wave. Mathematically, it's very, very easy to code, because it's just for every time increment, dt, you add on a certain amount. And as you add stuff on, you eventually get to a point where you've reached the maximum value that your output circuit is going to be able to achieve. You go all the way down to 0, or all the way down to the opposite value, and then you start counting up again. In fact, what I want to introduce here is S, which is the sampling rate, and Z here, which is the span. And the span represents the range of values that the digital to analog converter or some further mathematics is going to accept. So V, the voltage here, if we were to have a span of, say, -1 to +1, say a span of 2 volts, each step for the voltage we need to add twice the frequency divided by the sampling rate. 2 because we've got a span of 2 here. Then if the voltage is greater than 1, we need to add some logic. If the voltage is greater than 1, then we set the voltage to -1. But in fact, to keep this thing absolutely in tune and to do it perfectly right, when we add this next increment on here, it might actually overshoot slightly. So there's an extra little bit of overshoot here, n. So what we actually say is if the voltage is greater than 1, the voltage becomes -1 plus that little n bit. So instead of going exactly from here to here, we might actually go there. And that's how we code a sawtooth. And we'll look at the actual code in a minute. Now let's move on and have a look at a triangle wave, because that is very, very similar. Sorry about the continuity here, but I wrote something there and I had to move my window up. Again, we have the same thing. We have Z, which is our span. We have the little issue with N, where it rolls over. We have the difference in time, which is our 1 over the sample rate. The slope we have now, I didn't really talk about the slope in the last one, but the slope is basically the angle of this line. The slope in this one is actually twice the span times by the frequency divided by the sample rate. The reason it's twice is because in one cycle we have to go down and all the way back up again. For the saw wave, we only had the slope was from here to here. The logic is similar to the saw wave, but we have to have an if statement here, because when our voltage reaches the maximum, we have to take off the little bit n, as we saw before. This bit here, we have to take that off. But we also have to reverse the direction of the slope. The reason is when we get here, we start counting down. We don't go down to 0, we have to start counting down. And when we get to this point, the green, when we get less than the minimum value, we have to add n on, the little extra bit, and then we have to swap the direction of the slope, and then we have to start climbing up again. So triangle wave, we have the additional mathematics or additional logic of changing the sign of the slope. And also we have the fact that the slope has to be half as much, essentially an octave higher if we use the same slope as the saw wave. Right, so that's the sort of mathematics of a triangle wave. You'll see here that everything I write for the PiPico is written in the C language. Reason being, it's very efficient, and it's what we're going to need in order to get a good sample rate for our oscillator. This is the inner loop. This is the inner loop code for the oscillator. There's a number of variables like voice and amplitude and various other things, peak, which come from other places in the code, but we're not going to worry about those now. That's really for a later video. So the way the oscillator works is we start with a value which is 0, so the signal total. We decide what voice we're using, and then we loop around these loops to add on for each oscillator, because we've got 14 of them, the amplitude of the oscillator multiplied by whatever oscillator value we have, or the signal I. This is an array, so there's 14 different signals. This is the part of the code which tells us what type of oscillator this one is. This one is the logic, which says if the signal is greater than 65535, it becomes, you take away from it 131072, which is actually the span. So this one, which is a maximum value and then goes down, which gives us the saw wave. this one is the one that's slightly more involved, because we see when it reaches the maximum value of 65535, the signal loses, becomes taken away from 1310372, which essentially is that value of n, the little extra bit. And then we flip the slew in the opposite direction. TLS is a little extra variable here. TLS essentially flips in the opposite direction, and then the slew goes the other way. So this is our triangle wave. So if the voice is true, we do a saw. If it's not true, we do a triangle. And we loop round these for each of the for each of the oscillators. So where does this slew value come from? Because this looks like it's actually important. I here is the value of the oscillator, the oscillator's number, and oct here is the octave. So the slew values are actually built into the code. They're actually integers here. There's 109 of them, and they represent the full sort of 9 octaves of the musical scale. So we can see that if we have oscillator, the octave set to 0, and oscillator 1, then we're going to select an oscillator 0, we're going to select 45 for the slew, and then we can go all the way up here to 12789. So these values here I calculated from a separate piece of code, but since this video is getting very long, I won't show you that now. But these represent the correct frequencies for the musical notes. There we go, that's our first look at some code. And what we see at the end of here is when we've done all the maths around 14 oscillators, we finally have a value of the signal total, which we can go on and do other stuff with. Here's quite an important point about the calculating. Within the space of dt, which represents our sampling rate, we have to come up with the next sample. We have to come up with a number. We have to come up with a number which represents the next step in whether it's sine wave, square wave, or whatever. But if we do a gigantic amount of mathematics, and by the time we finish the maths, we've got our next value, but it's too late, then our waveform is either going to be distorted or we're going to be out of tune. The issue you have with a microcontroller is that they're not very powerful, so we don't have a lot of CPU power in order to calculate this. But a more powerful computer, we've got issues where we actually have an operating system, and that might come along and steal lots of CPU. But yeah, in terms of getting stuff done, they're extremely good because there's nobody else hanging around causing delays in the system and basically stopping that from happening. But the one problem I struggle with is how do I determine if this has happened? I mean, if I put too much maths into the oscillators, how do I know that this is actually occurring? Because I could print something on the screen to say, oh, it's too long. But the very act of printing stuff on the screen will delay the whole process. Here's a little bit of pseudocode that explains my thinking in terms of how to create an oscillator. So what I do is I look for something called wanted time. Wanted time is when I'm going to need the next sample. I set wanted time to be now, and then I loop forever, so my oscillator is going to run forever. So whilst the wanted time is less than now, so now is the time that I measure immediately now in the code, I sleep. Well, we've already set wanted time to now, so it's just going to drop through. Once it's dropped through, I added on to the wanted time dt. dt is our 1 over the sample time. Then I do my mathematics, and then I come around again. And while the wanted time is less than now, so if I haven't done very little bit of maths, I've still got time to sleep. Then I drop out and then I do some more maths. But what I do inside this loop here is not only sleep, I also count. And if my count drops out to be, let's say, less than 2, so it's only ever slept twice, then I know that I haven't counted enough in this loop here. I haven't slept enough, which means I've done too much maths. And in this case, I need to light up an LED or do something to warn me that all this mathematics that I'm attempting to do with filtering and wave shaping and anything else, it's just become too much. I need to wind it back. There we go. That's essentially how I code an oscillator on a microcontroller. There's a small amount of sleeping, and if there's no sleeping, there's a problem. Great. Well, if you're still with me, we've talked about the oscillator. We've talked about the voice. We've talked about how by adding 12 into that array we can increase the octave. What we haven't talked about yet is the wave shaper. So these 4 things which I put together really make up the 14 oscillators in terms of the code. So let's talk a little bit now about the wave shaper and see what that sounds like and how it works. I want to talk about the wave shaping because it's something I've been doing a lot on a lot of the inner loop videos. It really makes up for quite a unique sound. So let me just draw a waveform. Let's draw an axis. And talk a little bit about what the wave shaper does in this device. So let's imagine we've got a nice clean sine wave. What we're going to do is come along with our Fender or some valve amplifier, and we're going to overdrive it. When we overdrive it, our nice clean sine wave is actually too loud for the electronics. And what that does is it causes our sine wave, if we've got a good valve amplifier, causes our sine wave to sort of nicely kind of cut off, and kind of squares the sine wave off, and it's all very beautiful. But that's not how it works for my wave shaper. So let's get rid of this beautiful fuzz. Back to our beautiful sine wave. What my wave shaper does is it says, let's again choose some threshold, make it orange this time. Draw in our threshold here. So at this point in the amplitude, we're going to do something. Well, I'm not sure you can actually do this with. I'm not sure if you can actually do this with any kind of analog device. Which is, we know here, it's green line. This is the maximum capability of our analog to digital converter or whatever. And here's our yellow line, which is the sort of threshold that we're going to think about. And what we're going to do is say, when we get to this threshold, instead of going flat here, let's say, oh, please go there instead. And when you get here, please go here. So instead of clipping the signal off when it gets too loud, we're actually clipping the signal before it gets too loud based on this threshold here. So I'll put the threshold value here in blue. So if our signal gets larger than this threshold, then become a square wave. In this way we can really distort the signal, a sine wave, in some quite peculiar ways. Let's just quickly look at that against the triangle and saw waves. Here comes our triangle. It's going to go up. It's going to go down. It's going to go up again. I'll put in that green threshold line again. And now you can see. Now you can see that by hitting the threshold, we're making a kind of combination between a triangle and a square. I'll pop the sawtooth in, just as a matter of interest. So the saw starts down here. It goes up here. And then it goes down to there again. It goes up again. The saw is going to go like this. So it's going to add some curious shapes to the waveform and make it sound really different. So let's have a little listen to that, and then I'll talk about some more. There's one more part to the wave shaping. You've seen me twisting the knob for the threshold value. Here's our threshold value. But this time, instead of peaking out here or here, when we reach this point, let's go somewhere else. Let's actually go below. So now what happens is our waveform actually looks like this. We go up, we hit the green, which is the threshold point, we go to the peak point that we've defined, and then we return, and then we go down. Same again, hit the green point, we'll go to the peak point, and return. And since this purple value could even be here, our waveform could even at this point go all the way down here and back. And if this one's done the same, it actually kind of doubles the frequency. It's turned into a wave folder. So let's have a quick listen to that as well. Here we are back to the code. Just have a quick look at that wave shaping function, and that actually lives here in two if statements. So t is the signal value after the oscillator, and if t is greater than the cutoff value, which was our green line, then t becomes the peak value, which was our purple line. If t is less than minus cut, t becomes minus peak. The values of cut and peak relate to the potentiometers, and you could see me twisting those. Cut value is the left-hand potentiometer, or the one on the extreme left, and the peak value is the middle one. This is my favourite kind of wave shaping, and I'm not sure how easy this kind of wave folding functionality is to do with an analog device. And I think that's what makes it somewhat unique. So there's the code. I know this has been a long video, but there's been lots of people asking to see more details of the code. I really haven't held back, and I've gone in as much depth as possible to really cover the main aspects of just the oscillator. In the next one I'm going to talk about the output stage, so the mixer, the filter, and I may even touch on the hardware if it doesn't get too long. So keep an eye out for part 3 of the PicoDrone. Thank you very much for watching, and I'll see you next time on the Inner Loop.